My name is Mikko Kuisma. In this video we will demonstrate how to use heat flux sensor to measure pulse from the artery. We start with a background info about the heat flux sensor since the sensor is not widely known. Then we briefly introduce mechanics behind the measurement and show how we build the setup. In the last part of our demonstration we will show some results and compare recorded waveforms to the ECG recorded simultaneously. Nowadays we have many sensors and methods to measure temperature, but only few to measure heat or heat flux. Heat flux describes the transfer of thermal energy, heat. Heat is transferred by means of conduction, convection or radiation. One of the differences is that the temperature is scalar and the heat flux is a vector. The heat flux has a direction of energy flow. The heat flux sensor differs from the temperature sensor in the sense that instead of measuring the actual temperature, the heat flux sensor measures the flow rate of thermal energy through the sensor. Heat flux is commonly measured by monitoring the rate of conductive heat in a thermally insulating medium. The most straightforward way to perform heat flux measurement is to use two temperature sensors. Heat flux can be defined by measuring the temperature difference over the material with known thermal conductivity. The heat flux can then be indirectly calculated. However, this is impractical in many cases since the temperature sensor is measuring local temperature spot and the thermal conductivity of the media must be known. A commonly used structure inside the heat flux sensor is a thermopile. A thermopile is a thermoelectric transducer comprising of a stack of thermocouples. The hot and cold side contacts are at the opposite sides of the sensor. Thermocouples inside the sensors are thermally in parallel and electrically in series. The temperature gradient to be measured by the sensor is directly transduced to an electrical signal. The heat flux sensor also indicates the direction of energy flow. Another advantage of a temperature measurement is that the heat flux sensor changes instantly when temperature changes takes some time. Long story short, temperature is the integral of the heat flux. Typically, the sensor operation principle is based on the thermoelectric Seebeck effect. There are also other types of constructions, materials and operation principles of heat flux sensors. Recently, we have developed a silicon-based MEMS sensor here at LUT University. Antti will tell briefly about our work.
Application requires robust and low-cost heat flux sensors. We are working with several heat flux sensors. One of the designs is a mass-producible MEMS sensor. We have also been designing and assembling the experimental test setups and instrumentation electronics here in Lappeenranta.
Another well-studied heat flux sensor is the gradient heat flux sensor. We have studied sensor materials, structure and the use of sensor in various applications. Professor Mityakov from St. Petersburg, Russia will tell briefly more.
Gradient heat flux sensors are based on transverse Seebeck effect. Heat flux through anisotropic material generates thermal power. By selecting materials with anisotropy, we can optimize thermal and electrical properties of the sensors.
The heart rate is widely recognized as the most important vital parameter of wearable measurement. Our team proposes the use of heat flux sensor in pulse and heart rate measurement. One way to implement heat flux-based pulse monitoring system is by placing a heat flux sensor directly on the radial artery as shown later in this demonstration. The pulsatile blood flow generates pulsatile heat flux. Generate signal is similar to typical pulse pressure and PPG waveforms. Optical heart rate measurement (PPG) is typically the wearable heart rate measurement technology of choice. A gold standard of heart rate measurement is the measurement of the electrical activity of the heart, known as electrocardiography (ECG). Typical ECG and PPG sensor signals is shown in this picture. We used a commercial GreenTech heat flux sensor in our setup. The sensor size is 10 by 10 mm and the thickness of the sensor is half a millimeter. The first thing to do was to attach a heatsink to the sensor. This improves the sensitivity. I used a conductive thermal tape to attach the sensor. This same tape was also used to attach the sensor to my skin. The sensor was placed on top of my radial artery in my left hand. Here you can see the sensor attached in my hand. In this close-up you can see my pulse is moving the heatsink and the sensor combination. The voltmeter in the background shows the fluctuating signal from the sensor. You can see that the movement causes some artifacts and the signal is not constant. To improve signal quality and tackle the movement artifact, we also use this medical tape. As a reference sensor, we use the Beat the Phone EGC chest strap with a sensor. This sends the sensor data directly to the smartphone screen. The heat flux signal was directly connected to the digital multimeter. The sampling frequency of the multimeter was 50 Hz. There was no amplification between the sensor and the multimeter. The live EGC data from the chest strap can be seen on the smartphone screen on the lower left corner. Now we can start the measurement. I will try to keep my hand as still as I can. You can see the pulse waveform on the top of the screen. The signal is quite similar to the typical PPG signal waveform. If we now freeze the frame, put the EGC on the top of the heat flux pulses, zoom it in a little bit, position the waveform into the right place, we can see matching EGC and heat flux pulses. Even if I try to keep as still as I can, you still can see the heat flux signal fluctuating. The autoscale function of the meter hides the pulse signal now and then, since the movement causes signal fluctuation. If I now move my hand, you can see the signal level change caused by the movement artifact. This looks quite the same than in a typical optical PPG measurement. Here you can see recorded heat flux waveform. The length of the signal is 10 seconds. The voltage scale is 2 millivolts per division. You can see my heart rate was quite high since I was so excited that I was drinking too much coffee. The shape of the signal is quite similar to this typical PPG or pressure waveform. It has two parts with diastolic and systolic peaks. If we look even closer, we can see the pulse peak-to-peak value to be 2 millivolts. The signal you see here is raw data directly from the multimeter. It's unfiltered and sampled at 50 Hz. To show you that this was not a trick, I will now show you the disassembly of this setup. The only change I did during the setup that I changed the heatsink. The heatsink used in the final measurement was a little bit larger than you saw in the setup video. This will give a little bit higher signal level. It also prevents the fluctuation or drift of the output signal, since the heatsink temperature in a larger heatsink it stays more constant. When I detach the sensor, you can still see that this acts as a heat flux sensor. After some button pressing, you can see the signal change the direction, since I changed the direction of the heat flow. Increased attention has been directed at developing new wearable measurement methodologies. Because of the difficult implementation of the ECG in wearable form factor, heart rate has conventionally been measured using optical sensors. However, the PPG technology usually relies on external excitation by light-emitting diodes. The LEDs consume electric power and therefore shortens the device's battery life. One advantage of proposed method is that the demonstrated measurement was totally passive. In practice, we need some amplifier front end, but there still is no need for external excitation. Another advantage is that the heat flux signal can be used to measure energy. This can be an advantage if we try to improve the human energy expenditure estimation, meaning calories consumed. As we reported in our previous study, we can measure calories and improve the estimation with a heat flux sensor, especially at rest. The heat flux sensor can measure pulse waveform. This was also verified with the ECG sensor. However, the signal-noise ratio should be increased. The placement of the sensor also needs to be studied. Now it was placed directly on top of the radial artery. Effect of the heatsink also needs to be considered. The coupling mechanism of the pulse waveform is still unclear. This might be just one other way to make a ballistometric measurement of the pulse waveform. Thanks for watching. Check also our other studies where you can find other heat flux sensor applications.